All right. So I made like a dozen videos already, and then I realized maybe I should actually make a video kind of being a little bit more explicit about the postulates and the common notions. I didn't previously make this video because I thought that anybody that might be coming across these videos like already knew these, and maybe they're really obvious. I mean, they are. That's the entire point of the postulates and the common notions, is that they should be really obvious. But I figured that probably for completeness, it would make some sense that I should make this video. I don't think I'm going to make a video going through all of the definitions, on the one hand, because every single book of the elements, well, maybe not every single one of them, but different books have definitions, so there would be a lot of them. And I think that the definitions, they're all pretty much things that I think anybody would already understand, right? A straight line is a line which lies evenly with the points on itself, defining things like that. So, and in general, I think if I come across some of the strange language that they use in the postulates or in the propositions, I just define them in the video. But yeah, here's the video for going through the postulates and the common notions. So, again, postulates and common notions, I kind of think of them, group them under the umbrella term of the axioms. These are the axioms that Euclid uses to build up everything in the elements. And the difference between the postulates and the common notions is that the postulates are strictly geometric axioms. Common notions are axioms that can kind of be applied more broadly. So, at least for what that meant for the Greeks, is that they would be applied to numbers. So, common notions are just kind of like general mathematical truths. Postulates are specific to geometry. And there are 5 of each. So, let's go through them. We'll go through them one at a time. So the first one, the first postulate, is to draw a straight line from any points to any other point. So just saying that, like, if you have 2 points, you can draw a line between them. That's all that is being claimed there. So again, like, super obvious, right? Stuff that, and that's the point of axioms. Axioms are claims that should be so simple and obvious that they just don't even require a proof. That anybody would just take them and be like, well, yeah, I mean, that seems really obvious. If you have 2 different points in the plane, yeah, I can draw a straight line through them. Yes, of course. I don't need to prove that. Postulate 2 says to produce a finite straight line continuously in a straight line. So all that that's saying is that if you already have a line, then you can continue that. You can produce the line, like lengthen the line indefinitely. You can just keep drawing the line as long as you would like. So it's all that that's saying is that if you have a line, you can make it longer. That's fine. Again, super obvious. Doesn't even require a proof. The third postulate is to describe a circle with any center and distance. So all that this one is saying is that if you have some center and some line segment, you can create a circle with that center and a radius of that line segment. That's all that it's saying, is that, yeah, we can create circles. That's pretty much what postulate 3 is saying. Postulate 4 says that all right angles are equal to each other. Again, just really feels very obvious. Why would you ever need to prove that? It almost feels so obvious that you don't even, like, you might even be like, well, why does that even need to be claimed? And it is kind of interesting that, you know, there are certain things that Euclid felt were necessary to claim and to, like, explicitly state. And then now, today, a few thousand years later, we also can look at it and see where there are assumptions that he made that he didn't put into the postulates, or he didn't formalize, because they were apparently so intuitive. And I think that's interesting, because I don't think that it's the case that Euclid actually took some of those things for granted. Like, for instance, that there are some propositions where you have 2 circles that you create, you construct, and to us, it's very intuitively obvious that those circles will intersect. And Euclid states that as part of his proof. He'll be like, oh, like, create these 2 circles and then name their intersection point C or whatever it is. And without really him stating explicitly that, yeah, these 2 circles are going to intersect somewhere. And I think that that's something that he probably knew that should probably be justified. So I think that it's interesting that certain things like that are omitted. I sort of have a feeling that it may have been the case that he just felt like to lay out all of those assumptions would be too burdensome. Today we don't consider that burdensome at all. We consider that good math. But I think that back then, because to me, even more than being this incredible mathematical thinker, I think that Euclid was an incredible mathematical teacher. And I think that he realized that he needed to keep everything as simple as possible for this to work. Okay, so then the very last postulate is the most famous of Euclid's postulates. It's called the parallel postulate, postulate 5. And just before I sort of unveil postulate 5, take a look at each of these postulates. They're quick. I mean, just one line basically, a couple of words, and they are so intuitively obvious that you might have up to this point been like, why does this even need to be stated? It's so obvious. But then take a look at postulate 5. Postulate 5 says that, and I'll read it first in the language that it's written, and then I'll sort of give my quicker interpretation and maybe make a diagram of it too. So it says that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which are the angles less than two right angles. Lighting looks a little bit funny there. Maybe that's better. Okay, so what on earth is that saying? First of all, just notice how long this postulate is compared to the other ones. It's not simple. It's not just like a quick, boom, 2 points, you can make a line sort of postulate. It's like, well, if you have this, and then if you have this, and on top of that, if you have this, then this follows, which feels less like a postulate and much more like a theorem, which for a very, very long time, people thought of it that way. They thought, there is no way that this is a postulate. People thought for a really long time that you could prove postulate 5 just with the first four postulates. Not necessarily just using those first four postulates, but the first four postulates plus all of the propositions that follow from those first four postulates, that they felt maybe you could use all of that to prove postulate 5. And time and time and time again, they failed. And the reason that they failed, they didn't, fail outright, a lot of people thought that they had done it. They thought that they had omitted postulate 5, and then they were able to prove postulate 5 based off of postulates 1 through 4 and the propositions that result from them. And time again, what ended up happening is that somebody would come along and look at that proof that was, somebody thought was proving postulate 5, and they would see that there was some assumption that they used in there that was actually equivalent to postulate 5, meaning it was like a circular argument. It wasn't actually proving postulate 5 because they were assuming postulate 5 in order to prove it. So, and that's not how logic works. You have to, if you want to prove a claim, you have to prove it without citing the claim itself. The most famous of those attempts, by the way, was from Playfair. And I didn't look before this when he was around. I want to guess, this is just totally a guess, 1500, 1600? I'm not sure. I might be completely off about it. But Playfair's axiom, what Playfair stated was, he said, all right, well, rather than postulate 5, let me try to rephrase this. Here's a different postulate that is simple, that is more obvious. And he said that if you have, and I'll just kind of draw it lightly here because I want to erase it because it's not the big point of what I'm trying to say. Playfair postulated this. He said, if you have a line and you have some point that is not on that line, then there exists exactly one line that passes through this point, which is parallel to the given line. And Playfair stated that as a postulate. So, and that does kind of make more sense. That's a lot simpler, and it does seem at least more obvious than what Euclid wrote out. And today, that's generally taken to be the definition of sort of parallel lines and the parallel postulate. That's taken to be the parallel postulate. But it turns out that that is exactly equivalent to what Euclid wrote out. And it was proved in maybe, I don't know, the 1800s that postulate 5 cannot be proved. It does have to be taken as a postulate. So again, let's go back to it and see what it's actually saying. All right, so that if a straight line falling on two straight lines, so here's my two straight lines, and now I'm going to make another straight line, which today we might call a transversal. So here's my straight line falling on two straight lines. Postulate 5 says if this straight line falling on the two straight lines makes the interior angles on the same side less than two right angles. So we're looking at like these angles right here, angle 1 and angle 2. And the claim of postulate 5 says that if angle 1 plus angle 2 is less than, so strictly less than, two right angles, which today we would say, instead of saying two right angles, we might just say 180 degrees. So if angle 1 plus angle 2 is less than 180 degrees or less than two right angles, then the implication is that, let's see, I had better name my lines. I'll call them L and J. So if angle 1 plus angle 2 is less than two right angles, then L meets J on the same side of, and I'll name my transversal, I'll call it K. L meets J on the same side of K as angles 1 and 2. That's what it's saying. So it's saying if you have this situation where angle 1 plus angle 2 is less than two right angles, if I was to just produce L and J forever, they will somewhere over here, they will intersect. And this is the parallel postulate, because it's basically saying that if you have this, but it's on both sides of K, then L and J are going to be they're going to be parallel to each other. If it is the case that angle 1 plus angle 2 is not less than two right angles, and then angle 3 plus angle 4, oops, that's not a 4, angle 3 plus angle 4 also is less than two right angles, then L and J are parallel. So that's the parallel postulate. Really, really, really famous postulate. Yeah, for all of the above reasons. Okay, so those are the 5 postulates, and then we'll go through the 5 common notions. There's not anything as interesting in the 5 common notions as the 5th postulate, but we'll go through them anyways. They're nice and quick. So common notion 1 says, things which are equal to the same thing are also equal to one another. So kind of written symbolically, this is saying that if A equals C and B also equals C, sorry, I was about to get confused about with another one. If A equals C and B equals C, then A equals B. So since A is equal to C, A and B are both equal to the same thing, they're equal to each other. So it's the transitivity of equality is really what that is in sort of today's language. All right, common notion 2. If equals be added to equals, the wholes are equal. Okay, yeah, here's the one that I was about to write out. So it's saying that if A equals C and B equals D, then A plus B equals C plus D. Right? If equals be added to equals, the wholes are equal. Yeah. And then common notion 3 is kind of the same idea, but with subtraction. If equals be subtracted from equals, the remainders are equal. So again, if A equals C and B equals D, then A minus B equals C minus D. Equals subtracted from equals are equal. All right, common notion 4, things which coincide with one another are equal to one another. And yeah, this is kind of an interesting one. This is sort of like a superposition argument. I guess this one is, to me, this still feels somewhat geometric in nature. over more than like these first three common notions. These ones can be applied pretty much anywhere in math. This one does feel a little bit more geometric. And it comes up in, let's see, he uses this in proposition 4 because proposition 4 is a superposition argument. So things which coincide with one another are equal to one another. So if we have that, the point, so you can think of these as points. Again, if A equals C and B equals D, then if we think about the line AB, which maybe looks like this, here's A, here's B, well, if A is also equal to C and B is also equal to D, what this is saying is that the line AB is the same as the line CD. So that's what common notion 4 is saying. Common notion 5, the whole is greater than the part. And this one comes up a lot with like angles. So if we have some angle like this, ABC, and then maybe on the inside of ABC there's also this other line right here, extends out to D, then the claim is that, well, this whole angle is ABC, so angle ABC is greater than the two smaller angles that make up ABC, because ABC could be thought of as ABD plus DBC. So it's just saying that angle ABC is larger than both of those. So angle ABC is larger than angle ABD, and the implication, too, is that ABC is larger than angle DBC. So the whole is greater than the part. And it's kind of something of a shaky assumption, I think. It's pretty intuitively clear, but it's also one that probably does require, like by today's standards, maybe a little bit more justification than like the first 4 common notions required. So in any case, there's the common notions and the postulates, and yep, the video is not totally synced up with what I'm saying. I need to figure out why that's happening. I'm not super techie with that. All right, there's that.